So I know how much you were looking forward to class today, and it would seem that Mother Nature has made that impossible. And so I've decided to try and reproduce the class that we were going to have today through this video. Um, I think that by doing this, I hope that it'll help you understand what's in the notes. I'm going to post this note on Unified Classroom, so you'll have access to all of the notes, but I thought it might be a little easier for you to understand if I try to walk you through it. And that way we hopefully won't get too far behind and we can try and stay on schedule for this AP course. So the objectives that we were going to try and cover today in class were threefold. The first was to interpret the meaning of a derivative. The second was to estimate the derivative of a function at a point if we're given a table of values. And the third is to learn how to use the numerical capabilities of a graphing calculator to find derivatives. So those are the three things we're going to try and do today. And I hope that once this video ends, you'll be able to go back to the beginning and feel like those three things have been accomplished and that you understand these three topics. So without further ado, let's move on. The meaning of a derivative. Well, let's start by thinking about this question. Suppose that for the function y equals f at x, we know that f at 5 equals negative 3 and f prime at 5 equals 2. So let's just stop for a second and just think about what we've read so far. Y equals f at x is our function. F at 5 equals negative 3. Well, that just means that the function, the curve, whatever it is, goes through the point 5 comma negative 3. And f prime at 5 equals 2, you'll remember this from the last class. This means that the derivative of f at 5 is 2, or in other words, the slope of the curve at 5 is 2. We can rewrite f prime at 5 equals 2 better this way, saying that dy dx, the derivative of y with respect to x, when x equals 5, is 2. And the question is, what does that mean? And it's not such an obvious question. There's a few ways that we can look at this. If you remember back to the last class, we said that the derivative gives us the slope of the tangent. And so we could say that the slope of the tangent to y equals f at x equals 5 is 2. Let's be really clear about this. Oftentimes people make the mistake of saying the slope of the point is 2. Well, a point doesn't have a slope. I mean, you can imagine that. Just imagine a point sitting off in space somewhere. It doesn't have a slope. So points don't have slopes. Curves have slopes and tangents have slopes. And since we're taking the slope of a curve here, of this curve y equals f at x, we have to specify where we're taking that slope because it changes. And so we're saying that we're taking the slope, in this case, at x equals 5. So we say the slope of the tangent to the line tangent to the curve y equals f at x equals 5 is 2. Likewise, as we just said, we could also say that the slope of the curve y equals f at x equals 5 is 2. In fact, that's really why the first one matters. We're not really too interested in the tangent itself, except that the tangent has the same slope as the curve. And it's the slope of the curve that we're really interested in. A third way of saying that is to say that this represents the rate of change. We know that a slope gives us a rate of change of a line. And so in this case, we have the rate of change of a curve. We say the rate of change of y with respect to x when x equals 5 is 2. Graphically, we could express this as follows. And we see here we've got some curve, this red curve, y equals f at x. We really have no idea what this curve looks like, except that it goes through the point 5 comma negative 3, and that at the point 5 negative 3, it has a tangent with a slope of positive 2. So the curve must be increasing since the tangent line has a slope of 2, and so maybe the curve looks like this red thing, but it could also be concave up. It could be doing a lot of different things. We don't know. All we know is right in here, it must look like this. Now let's get a little farther into talking about what this means. We say that the slope of the tangent at x equals 5 is 2. So what does that mean? Well, that means if we're at the point 5 comma negative 3, if we're right here, if I go 1 unit to the right, the tangent goes up 2 units. That's what slope means. Rise over run is 2. In other words, if we run 1, we rise 2. And that's exactly what that is for the tangent line. But the problem is, to talk about the curve, we see that it's not exactly true for the curve, is it? If we go 1 to the right from this point 5 comma negative 3, the tangent goes up 2, but the curve goes up less than 2 because the curve is bending away from the tangent line. And so as soon as we get off this point, the rate of change is no longer 2. So if I go over 1, the curve goes up a little bit less than 2. But I guess I could say that when I go over 1, the curve goes up approximately 2, something along those lines. A better way to say it is, well, why do I have to go over 1? Would it be better for me to say if I go over 1/10, the curve goes up 2/10? Still not exactly right, but you can see that if I zoom in on this enough, that right in this area, the curve and the tangent line go up about the same amount. And so rather than going all the way over 1, if I just go over 1/10, then the red line and the purple line are going up about the same amount. And so in general, I could say, one further example. What if I said, instead of going over 1, I now go over 1 pixel? The least amount I could go over on the screen. Well, if I go over 1 pixel, then the curve and the tangent line are going up almost exactly the same amount, 2 pixels. And so the way I can say this is that at x equals 5, a very small increase in x, which we call an infinitesimal increase in x, an infinitely small increase in x, will produce a 2 times that increase in y. Notice the difference. I'm not saying that it will produce an increase in y of 2. It will produce an increase in y that's twice the size of the increase in x, as long as I don't get too far away from 5. Obviously, if I go from 5 over here to 10, the curve is not going up anywhere near 20. But that's too far. But if I go a very small to the right, then the curve goes up about twice that small amount. Okay? Another way of saying that, perhaps an easier way of saying that, is to say that when x equals 5, y is increasing twice as fast as x. Okay? So what we're talking about here is on the curve, a very small change in x produces a 2 times that increase in y. In this case, because the derivative is 2. Does that make sense? Let's think of it in terms of an example. Suppose that I have this. I'm given a prime at r, and I'm going to tell you, because a prime at r is sort of non-specific, I'm going to tell you that a prime at r means dA dr, and I'm going to tell you that in this example, a represents area and r represents radius. So maybe we think of something like a circle. dA dr is the rate of change of area with respect to radius. And suppose I give you this. dA dr such that r equals 3 equals 21. And my question is, what does this mean? Well, we could go back to those 3 things in purple at the top. We could say the slope of the tangent to A when r equals 3 is 21. We could say that the slope of the curve, y equals a at r, when r equals 3 is 21. Or we could say the rate of change of A with respect to r when r equals 3 is 21. Perhaps a better way of thinking of it is when the radius is 3, an infinitesimal increase in radius will produce a 21 times that increase in area. Or I can say that when the radius is 3, the area is increasing 21 times as fast as the radius. And that's probably the best way to think of it. What does it mean? It means that when the radius of this is 3, let's give this some units. Let's just pretend that the radius is in centimeters and the area is in square centimeters. What this means is that when my circle has a radius of 3 centimeters, if I move over to the right 1 centimeter, my area will increase by about 21 square centimeters. Don't confuse this with thinking that the area is 21 square centimeters. That's not what it means at all. What it means is that whatever the area was when the radius was 3, it will be about 21 square centimeters bigger if the radius increases to 4. Of course, it won't be exactly 21, because when r goes from 3 to 4, that's kind of a big jump. Just like over here, when I said if x goes over 1, the curve doesn't go up 2. The curve goes up less than 2 because it's bending away. The line goes up 2. The tangent line goes up 2, but the curve only goes up a little bit less than 2. Same is true here. When r equals 3, if I go over to r equals 4, the tangent line would go up exactly 21. The curve will go up a little bit less or a little bit more than 21. A little bit less if the curve is bending away from the tangent line, and a little bit more if it's concave up, and the curve is bending up from the tangent line. So I can say, instead of when the radius is 3, I shouldn't say that if the radius goes to 4, the area goes up 21. That's kind of a big jump. But I could maybe get away with saying, if the radius goes from 3 centimeters to 3.1 centimeters, then the area increases by 2.1 square centimeters. That would be better. Or if the radius increases from 3 to 3.01 centimeters, the area increases by 0.21 square centimeters. That would be even better. Okay? A very small increase in radius, when the radius starts at 3, will produce 21 times that change in the area. Does that make some sense? Let's go on and look at another example. In this case, I've got v prime at t equals dv dt. And I'm telling you that in this case, v doesn't represent volume, it represents velocity, and t represents time. And I'm going to give you the units. We're going to say that the velocity is in meters per second and the time is in seconds. And we're going to think a little bit about these units because I want to go back to the previous example, which is not so obvious. In this case, I tell you that v prime at 7 equals -3, but remember, we don't really like this notation. It doesn't tell us what v is changing with respect to. So we rewrite it over here in red in better notation. And we say dv dt such that t equals 7 equals -3. In other words, the velocity is decreasing 3 times as fast as the time increases when the time is 7. Okay, another way of saying that is to say that when the time is 7, the velocity is decreasing at a rate of 3 meters per second every second. In other words, 3 meters per second squared. And because we know from physics that 3 meters per second squared, that the rate of change of velocity is just acceleration, we could say that this means the acceleration is -3 meters per second squared. Let's go back and just think about the units of that previous example because it illustrates a really important and kind of tricky point. If I was to put units in here, if I said, like we talked about before, if I said that the area here was measured in square centimeters and the radius was measured in centimeters, then what would the units of this 21 be? Well, the units of the 21 would be change in area divided by change in radius. So that would give us centimeters squared over centimeters. Now, a lot of people are tempted to say, well, centimeters squared over centimeters just gives us centimeters. And in general, that's true. But in this case, it doesn't make any sense. The correct units of this are 21 square centimeters per centimeter. Because if you think about what this means, what it means is that when the radius is 3 centimeters, if I increase the radius, the area increases by 21 square centimeters. In other words, the area is increasing at a rate of 21 square centimeters per centimeter increase in radius. Therefore, 21 square centimeters per centimeter. Every centimeter increase in radius produces a 21 square centimeter increase in area. If I reduce the centimeter squared to centimeters, if I reduce the centimeter squared over centimeters to just centimeters, this doesn't make any sense anymore. We would be saying that the area is increasing at a rate of 21 centimeters. That doesn't make any sense. Area can't increase by centimeters. Area has to increase by square centimeters. And so the units of this would be 21 square centimeters per centimeter because the centimeters are different. Okay? It's 21 square centimeters of area per centimeter of radius. So we have to be a little careful with the units. Now we can move on. The next thing I want to look at is how do we talk about derivatives if we're not given a function, if we're only given a table? You remember in the last class, we talked about finding the derivative of a function. And we had those formulas, the limit as h goes to 0 of f at x plus h minus f at x over h, or the limit as x goes to a of f at x minus f at a over x minus a. And I'm hoping that you use those formulas repeatedly in the homework from the previous class and that you're fairly comfortable with those now. But what do we do if we want to find a rate of change, if we want to find a derivative, when we're not given a function, so we can't use those formulas? Maybe all we're given is a table. In fact, that's probably more common. It's usually much easier to gather data in a table than it is to actually come up with a function that represents the data. So here's an example. The table below lists wind speed at 3 hours intervals one day in Dodge City, Kansas. The time t is measured in hours with t equals 0 being midnight. We want to use this data to estimate the rate of change, w prime at t, of the wind's velocity with respect to time at 9 o'clock in the morning, which represents t equals 9. Just take a second, have a look at the diagram, or have a look at the table rather. And we see here, across the top, we're given the times. This is midnight, 3 in the morning, 6 in the morning, 9 in the morning, and so on. And this is the wind speed. At midnight, the wind was blowing at 12.55 miles per hour. At 3 in the morning, the wind was blowing at 12.4 miles per hour, and so on as we go across. And what we want to know is, what is the rate of change of the wind speed at 9 o'clock in the morning? So let's start by taking a look at that. What we want to know is, what is the rate of change of the wind speed right here at 9 o'clock in the morning? Let's be really clear, this is not the same as saying what is the wind speed at 9 o'clock in the morning. That's really obvious. The wind speed at 9 o'clock in the morning is 15.32 miles per hour. We're not asked that. We're asked for, how is the wind speed changing? Well, if we look at what's going on around 9 o'clock, we would probably guess that the wind speed is increasing. It seems like the wind speed is increasing as we go across here. It goes from 12.57 up to 15.32 up to 16. So it seems like it's increasing. Now we have to be a little careful of that. One of the things that they really like to do in the College Board on the exam is they like to trick people into thinking that they know more about what's going on than they really do. If they give us a table like this, all we know is what's going on at 6, what's going on at 9, what's going on at 12, and so on. We have no idea what was happening at 7 o'clock in the morning or at 8 o'clock in the morning. And we have to be careful that we shouldn't assume that we're going from 12.57 to 15.32 in a nice straight line, increasing all the time. We don't know that. Maybe at 7 o'clock in the morning, maybe the speed was 20. It might have increased up to 20 and then decreased down here to 15.32. We really don't know. All we know is that at 6, the speed was 12.57 miles per hour, and at 9, the speed was 15.32 miles per hour. But because we're asked to calculate the rate of change, in other words, the derivative, in other words, the slope, at 9 o'clock, and we don't have a function, we can only do the best that we can do with the data that we're given. So there are 3 ways that I could estimate the rate of change of this wind speed. In other words, estimate this derivative or this slope. One way would be to look at these 2 points. I can say, well, let's think about what's happening between 9 and 12. And if we look at that, we see, well, the wind speed goes up about 0.7 miles per hour across those 3 hours, and we can get the slope of that secant line. Okay, 0.7 divided by 3 is going to be about 0.25 or something like that, 0.23. And so we could say, well, from 9 to 12, the average rate of change is about 0.2 or 0.23 or something like that. And we can say that's an estimate at 9. And that wouldn't be accurate, but it wouldn't be a bad guess. Another possibility would be to say, well, why pick 9 and 12? We could just as well have picked 6 and 9. We could have done this. And if we do that, we're going to see that here, the wind speed increases a little bit less than 3 over 3 hours. And so now we're going to find out that the change in wind speed from 6 to 9 looks like it's almost 1 mile per hour per hour. Again, just an estimate, but it's the best we can do because all we're given are these data points. A third possibility would be to say, since we want it at 9, let's take a point to the left and a point to the right. So we can do something like this. And if we look at that, we say, okay, we're going from 12.57 up to 16. That's a difference of about 3.5 across a 6-hour difference. So 3.5 divided by 6 is around 0.5. So that would indicate about 0.5 miles per hour per hour. Now, all 3 of those are average rates of change, which we're going to use to estimate the instantaneous rate of change at 9. Which one is right? Well, actually on the AP exam, we would accept all of those. So if we look at the first one in blue, we see that we've got 16 minus 15.32 divided by the run, which is 12 minus 9, and that comes out to decimal 227 miles per hour per hour. If we look at the orange one, from 6 to 9, we see this, 15.32 minus 12.57 over 9 minus 6. And that comes out to 0.917 miles per hour per hour. And if we use the green one, we have 16 minus 12.57 divided by 12 minus 6, and that comes out to 0.572 miles per hour per hour. And all three of those are acceptable. If we look at it on the graph, what I've done here is I've plotted these 3 points. So here's the point 6, 12.57. Here's the point 9, 15.32. And here's the point 12, 16. And I've drawn this curve, this purple curve in here through these 3 points just to estimate what the curve might look like. I don't really know. And if I look at my 3 approximations, the blue approximation is the slope of this secant line to the right side of 9. And I'm saying the slope of the blue curve is approximately the slope of the red curve, which is the tangent line. That's the one we actually want. Or I could use this approximation, the orange one, to the left of the point of tangency. And I could say the slope of this orange line is approximately the same as the slope of the red line. Or I could use a point on either side, like I've done here in green, and I could say the slope of the green line is approximately the same as the slope of the red line. You can see that all 3 of those slopes, the blue one, the orange one, and the green one, we could say that all of them are an estimate of the slope of the red line. None of them are correct. All of them are an estimate. But I think you can also see that one is clearly better than the other 2. This one. The third approach is better. And that's the one that we usually will go with. And that's called a symmetric difference quotient. And so if we use the symmetric difference quotient, we usually get a more accurate estimate. Now, on the AP exam, you could use any one of these 3 if it was a long answer question, and we would accept it. But if it comes in the multiple choice, they're probably going to use the third one because that's usually the best estimate. Okay? So we call that a symmetric difference quotient. It sort of makes sense that they would call it a symmetric difference quotient because if you think of the words, symmetric because we've taken a point 3 units to the left of 9 and then 3 units to the right of 9. So we've gone 3 on each side. And difference quotient, well, difference quotient means the quotient of 2 differences, and that's what we've got in all 3 of these. I have a difference, and then I have the quotient of it. So we have the quotient of 2 differences. And that's how we get the slope of the secant line. And the slope of the secant line is the average rate of change. And the average rate of change in this case can be used to estimate the exact instantaneous rate of change. And so when I'm asked for the rate of change, W prime at t, at 9 o'clock, I write that like this. I say W prime at 9, which again, written better would be dW dt when t equals 9, is approximately, and I'm going to pick this third one, is approximately 0.572 miles per hour per hour. In other words, I'm saying at 9 o'clock in the morning, the wind speed is increasing by about 0.5729 miles per hour for every 1 hour increase in time. Or a better way of saying that is the speed is increasing 0.572 miles per hour, or 0.572 times faster than the time is increasing. Okay, I hope that makes sense. The next thing I want to talk about is sort of unrelated to all of this, and that's how do we find derivatives on the TI-nSpire. Okay, it turns out that your calculator is very good for this, and I just want to show you how to do it. So let's look at this question. Suppose I've got this function f at x equals 2x times sine of x, and I want f prime at 0 and f prime at x. In other words, the derivative of the function and then the derivative at 0. You remember how we did that the last time? We would use that formula, limit as h goes to 0 of f at x plus h minus f at x over h. And then we would plug in x plus h for these x's, and then subtract f at x, and then divide that by h, and we would try and take that limit. But that limit for this question is going to be really, really difficult to find. Right? We don't have the 4 tricks that I showed you last class, the factoring trick, the expansion trick, all of those tricks that we tend to use in limits when we get 0 over 0. And of course, we're going to get 0 over 0 because we're letting the run go to 0, which is going to drive the rise to 0. But those tricks are not going to work here. And so we're a little bit stuck. Very soon, next week, I'm going to show you how to calculate derivatives like this without using the limits. But for now, we're going to have to use a calculator for this. So let me show you how we can use the calculator to do this. So I'll get my calculator up here. All right, let me just clear this off. The first thing we want to do is actually put the function into the calculator. So my function was 2x sine x, so I'm going to start by putting that in. 2x times the sine of x, and I'm going to store that, and I'm just going to store it into f at x because that's what it's called in the question. Okay, so 2x sine x is now in f at x, just like it tells us up here. Now we want f prime at x and f prime at 0. I would actually get f prime at x first. In other words, I would do part b first, and then use part b to get part a. So how do we do this? Well, two ways. One is to go into the menu, go down to the calculus menu. We come across here and we see derivative right up here at the top. And we could use that to calculate the derivative. And that would certainly work. An easier way is to go to the templates here. This is called the template button. And this has got the most useful commands in mathematics right here in this button. And if I scroll across here, I see there is my derivative button right there. And so I hit that. And it says, okay, the derivative with respect to what? Well, we want the derivative with respect to x. Of what function? Well, we want the function f at x that we just defined. And if I hit enter, it tells me that the derivative of 2x sine x is 2x cos x plus 2 times sine x. That's my derivative. And so that's the answer to part B. And now if I want part A, I could just go up and I could get this and say, let's get the derivative of f at x, but let's get it when x equals 0. So I'm going to use my such that button here. Very useful command. I want this derivative such that x is 0. And I find out that it's 0. Okay. If I wanted the derivative somewhere else at, say, x equals, I don't know, 1.2, it would tell me the derivative of 1.2. Another way I could have done that would have been to just go up and grab this function and say, calculate this function such that x is 0. Since I already know that this function is the derivative, it's going to give me the same answer. It's going to give me that same 0. Or if I did it at 1.2, I would get the same answer as I got up here. So any of those are fine. And if you go down the page, you'll see that I've just put a few screenshots into the notes so that you'll remember how to do this later. Okay? And that's pretty much it for today's class. There is some homework. Okay, review assignment, pages 92 to 95. So I would like you to go through those and try and have those answered for class tomorrow, please. And I hope that this has helped. If you have any really burning questions, you can feel free to send me a WhatsApp today. I'll be trying to check that all day. But hopefully the video will help you to understand this. Be sure that you get the review assignment done, and be sure that you get those quizzes that I put in AP Central finished by tomorrow as well. Okay, hope you're having a good day. Stay dry, and with any luck, I'll see you tomorrow. Bye.